Okay, picking up where we left off. Now I want to do problems from section K. Again, this is not in your book, but I'll provide this homework for you with the answers. Here it says use identities to find the exact value. Exact value simply means do not use a calculator. Of the four remaining trigonometric functions of the acute. They're talking about geometry again. Well, this is sine of theta, this is cosine of theta. Well, it's really simple. Cosecant of theta is the reciprocal. And if you rationalize, that's 2 radical 3 over 3. And secant of theta is the reciprocal, 2 over 1. Got it? And isn't tan of theta the sine of theta over cosine of theta? Wouldn't that make it radical 3 over 2? Oops, okay, out of space. I like to work downwards, but here I'm going to work to the side. I'm going to break the rule. Sine of theta is radical 3 over 2. Cosine is 1/2. Those undo each other, and it's radical 3. And wouldn't that mean that cotan of theta is the reciprocal? And if you rationalize, that's radical 3 over 3. Fairly simple. If they use identities, you must use identities. The same deal with this problem. I could say that cosecant of theta is simply 3 over 1. Done. I could say the secant of theta is the reciprocal of this, 3 over 2 radical 2. If I rationalize, I'll get 3 radical 2 over. This will be a 2 times 2, that's a 4. And I could say out of those two, tan of theta is the sine of theta over cosine of theta. That is, sine is 1/3, cosine is 2 radical 2 over 3. Those undo each other, and I'm left with 1 over 2 radical 2. And I could say that tan of theta equal, if I multiply by radical 2, that is radical 2, I don't like that, radical, that is radical 2 divided by 4. And that means automatically that cotan of theta is the reciprocal of this, which is 2 radical 2. You could put that over 1 if you wish. We normally don't write that. That's not a problem. Now, for most part in trig, they don't specify what to use. I want to show you 2 ways of doing things. The triangle is a key. Identities are very useful, but triangle is much more efficient. Use definition or identities. You have an option. Definition is the triangle. Identities you just derive to find the exact value. Again, acute. If I want to use identities, I want to show you how that works. Well, I know from this automatically the secant of theta is 2 over radical 2. If I rationalize, that is 2 radical 2 over 2, which is radical 2. But 2 radical 2 over, yeah. If I want to find the sine, well, now it's not that simple. It's not like number 22 or 24. I could use the Pythagorean identity, say sine squared of theta plus cosine squared of theta equal a 1. Sine squared of theta is plus cosine is radical 2 over 2 squared equals a 1. And I could say the sine squared of theta plus, this is 2 over 4 equal a 1. That's 1/2. And I could say the sine squared of theta is 1 minus 1/2, which is 1/2. And if I square root both sides, I would say the sine of theta is plus or minus 1 over radical 2. I can't take the negative because the angle is acute. And I would say if you rationalize, that's radical 2. And out of those two, I could say now that tan of theta is the sine of theta over cosine of theta. That is radical 2 over radical 2, which is 1. That makes the cotan of theta, the reciprocal of 1 over 1 is 1. And there I found all 6 trigonometric functions. The sine, the cosine, the sine, the secant, the tangent, and the cotangent. I have another option, and that turns out to be much more efficient. If I am to say this is the adjacent over the hypotenuse because it's a cosine. Draw the triangle and have the you have to make a call where theta is. If I call theta to be right there, then this is the opposite. The adjacent will be radical 2 and this will be a 2. And to figure out the missing side, I would say the hypotenuse squared is the opposite squared plus the adjacent squared. So 2 squared equals the opposite squared plus radical 2 squared. 4 equals the opposite squared plus 2. The opposite squared equal a 2. And if I square root both, okay, I'm getting ahead of myself, forgive me. It should be plus or minus, but in geometry, that length is allowed to be a 2. And let me just make sure I didn't mess it up. Yeah, I did mess it up. I thought something was wrong. Because no side could be equal to the hypotenuse. If I subtract 2 from both sides, I will get that 2 equal the opposite squared. If I square root both sides, the opposite will equal, it should be plus or minus. But in geometry and an acute triangle, I cannot have a side that's negative. Well, now that I have the triangle, I could say the sine of theta is the opposite over the hypotenuse, and the tan of theta is the opposite over the adjacent. And as you see, we get this, and of course you could figure out the secant, cosecant, cotangent once you have those 3. So, I'm going to choose this method. You could choose whatever you like. Since they gave us an option from 25 to 36, those are identical. If I jump to number 32, they give me the following. It looks a bit trickier than it actually is. So at first glance, you might think, wait a minute, I'm missing something. Well, you're not, because any quantities over 1, if you really think about it. So in this case, this is cosecant is the hypotenuse over the, let me see, associated with sine, the opposite. So the hypotenuse is 5, and if I call the angle theta right there, then the opposite is right there. To find the missing side, I would say hypotenuse squared equals 1 squared plus the adjacent squared, right? Because this side is the adjacent. So 25 equals 1 plus a squared. A squared equals 24. And if I square root both sides, plus or minus, I can't have that being negative yet. And this turns out to be 4 times 6. So that's 2 radical 6. And once I get that, things are really simple. The sine of theta is the opposite over the hypotenuse. The cosine of theta is the adjacent over the hypotenuse. And the tan of theta is the opposite over the adjacent. If you rationalize, multiply by radical 6 top and bottom. Radical 6 times radical 6 is 6 times 2 is a 12. And I'm assuming you could find the remaining trigonometric functions, right? The cosecant is the reciprocal, the secant, and the cotangent. Now, something to elaborate on I talked about but I didn't mention. If I call this angle theta, as far as theta is concerned, this is the hypotenuse, this is the opposite, this is the adjacent. So if I take the sine of theta, that is the opposite over the hypotenuse. If I take the cosine of theta, that is the adjacent over the hypotenuse. And if I take the tangent of theta, that is the opposite over the adjacent. If I label those instead of giving them, because it's going to become a bit confusing, if I label this side L is the opposite, M is the adjacent, and K is the hypotenuse. The sine is the ratio of L over K. The cosine is the adjacent, which is M over K. and tangent is the opposite over the adjacent. Now notice what happens if I go in there and call this angle beta. When I say, what is the cosine of beta? Do you see that the cosine of beta is the adjacent over the hypotenuse? And do you see that the sine of beta is the opposite over the hypotenuse? And the cotan of beta, isn't that the opposite over the adjacent? Let me think really quick. The tangent of beta. No, cotan of beta. Give me one sec. The cotan of beta. Oh, tangent is the opposite. So as far as beta is concerned, this is the opposite, this is the adjacent. Tangent is the opposite over the adjacent. Cotangent is the adjacent over the opposite. And what did we say about this? I just don't want to clutter this for the notes. We said that beta plus theta equals 90 degrees, if you recall. So beta is 90 degrees minus theta, or theta is 90 degrees minus beta. What that means, the sine of theta is equal to the cosine of 90 degrees minus, which is beta, right? There's beta. And the cosine of theta is the sine of, and what's beta? Again, 90 degrees minus beta. And the tangent of theta is the cotangent of 90 degrees minus theta. I keep on messing up. Beta is 90 minus theta. And similarly, I could say the cosine of beta is the sine of theta. And what's theta? Theta is 90 degrees minus beta. I could say the sine of beta is the cosine of theta, and that is 90 degrees minus beta. And the cotangent of beta is the tangent of 90 degrees minus beta. Now, to make this useful, there's an easy way of figuring out when this happens. Whenever you're looking at trig functions, and this is the remaining of the section, use fundamental identities or complementary identities to find the exact value. Do not use a calculator. Well, what do I notice? I notice I have two angles. The first thing you look at, are those equal? And since those are equal, well, I'm going to use one of those identities right there. I notice they're squares. So I notice the secant of theta is tangent, secant squared that is tangent squared of theta plus 1. So I could replace the secant squared by tangent squared of that angle plus 1 minus tangent squared of 28 degrees, and those cancel out and I'm left with a 1. You glance at this problem and you notice, are the angles the same? In this case they are, so no need to use complementary angles. But I know that this is the cotan of 25 degrees, and isn't cosine over sine the cotangent of that same angle? And any quantity minus itself is a 0. I get to number 6 and I notice there's something wrong. Those are not the same angles. So, in able to use this properly, the question is always, if I use complementary, are those equal? Do they add up to 90 degrees? If they add up to 90 degrees, I could eliminate one of them. It doesn't matter which one. Let's say this one. I could say cosine of 90 is the sine of 90 minus 40 degrees from the complementary, always the case. And that's the sine of 50 over the sine of 50 degrees, and any quantity over itself is a 1. Those angles are the same, no need to use complementary angles. I could use either or. I could say this is the tangent of 10 degrees times, isn't cotangent 1 over tangent of 10 degrees? And that would be a 1. Or you could say tangent is the sine of 10 degrees over cosine of 10 degrees times cotangent is the cosine of 10 degrees divided by the sine of 10 degrees. Wouldn't those two cancel out and those two cancel out? So it doesn't matter which identity you use, you will get the same result regardless. If I look at those two, I notice that this angle and this angle are not the same. Do they add up to 90? Well, 78 plus 12 is 90, so I have a couple of options. I could say this is the cotangent of 90 minus 12 degrees by the complementary angle identities that I just derived, and this is the cotangent of 78 degrees minus the cotangent of 78 degrees, and any quantity minus itself is a 0. And I look at my last example, I notice this is 25, but this is 65. So I would say this is the cotangent of 25 degrees. This is 1 over, isn't cosecant 1 over the sine? So that I don't have to derive complementary for cosecant, and that's the sine of 25 degrees. Now, since these are in sine, isn't this cosine of 25 degrees over the sine of 25 degrees? This right here, isn't that the cosine of 90 minus 65? 90 minus 65 degrees is 25 degrees times the sine of 25 degrees. And what do you notice? This cancel with this, and this cancel with this, and you're left with a 1. And the first homework assignment we have for section K, you're going to do numbers 11 through 53 odd. Those are a must. And on number 11 through 35, find the angle. That means you're going to use a calculator.